Okay, so the next part of this, we've talked about a basic types of energy. And when we talked about the paycheck analogy in class, we said that essentially work is where money comes from. So work becomes money. And the way that you figure that out, it's your wage in dollars per hour, right? Times the number of hours you work. And that's how much money you get. Therefore, that's how much work you do. Well, work is also where energy comes from, except now instead of dollars per hour, you're going to exert a force over, or so force times a displacement, so F delta X. That's a force exerted over a displacement, and that's going to be your work now. So let's talk about that a little bit. Okay, so work is done on a system by external forces. In this case, there's wind. Wind is doing work on the sail, and that's pushing the sail, giving it velocity. So work is causing, therefore, work becomes kinetic energy. It increases the amount of kinetic energy. This is a stupid little video. Work doesn't just happen on its own. It's got to have external forces. If you remind me, we'll watch this video in class. It's funny. For when I calculate work then, work is the force exerted over a distance. Force, of course, is measured in newtons. Distance is measured in meters. We get a newton meter, which is a joule. And a joule is always the unit for energy and work. It's the unit for both, and that we'll use that essentially all of this unit. Now, a couple quick notes. Work, when you put energy into a system, it's positive, and if you take energy out of a system, it's negative. So if I think about it, you do positive work when you work hours to get money. The government does negative work. They take money away from your paycheck. But couldn't you just say also that is being transformed into non-usable energy? Absolutely. That's what can get confusing with this unit. Either way is acceptable to describe it. You can think about kinetic energy when it's in motion becoming thermal energy. So ETH, right? It becomes friction. Or your kinetic energy can have work done by friction and that energy is lost. Both of these, although different, mean exactly the same thing, and you can explain them both ways. All right, so here's an example problem. We are doing all of these in class this unit. Sarah pushes a heavy crate 3 meters with a force of 70 newtons. This one's actually really easy. Work is force times distance. So she gives it 70 newtons times 3 meters, and she gives it 210 or she does 210 joules worth of work. What happens to that? Well, once it comes direct, if it's going at a constant speed, all that work she's doing is becoming thermal energy. We can also have forces being applied at angles, just like we did in Unit 2. And if we look at here, right, this direction, the x direction, is the angle that the force is actually causing the energy. Just like the x component causes it to move in the x direction, like we talked about last unit. So sometimes, not often, but sometimes we can say that instead of F force times distance, it's the parallel component or the effective component of the force, which is going to be FD cosine theta. That will not come up very often unless you have a force acting at an angle. So just to kind of think about that a little bit more, if I'm going straight, if the force is in the direction of the displacement, my work is force times distance. If it's anything less than 90 degrees, it's FD cosine theta. If it's at 90 degrees, technically my work is 0. If my displacement is to the right, but my force is up, that means I'm not actually doing work. I am not doing work because the force is not in the direction of the displacement. Now in this example, now we're counteracting the displacement, and if I think about angles greater than 90 with cosine, what is that? Well, that's a negative number. So if it's negative, I'm removing energy from the system. This is like pulling something to slow it down. You're getting rid of kinetic energy. And now here, Now we have a perfect 180 degrees, so the work is 100% negative because it's the cosine of 180, which is -1, and that's going to be negative work. So now you're doing work to remove energy from the system. So I got a quick check for you. Which force below does the most work? I have 8 newtons at some angle or 6 newtons right in that direction. Well, the cosine of 60 degrees will be a half. So although this is an 8 Newton force, this is about, it's only half of it is in the effective area, so that's 4 newtons. This 10 Newton force, I didn't actually say it, this is going not at all in the direction of the displacement, so that's actually 0 newtons, and then this one is going to be 6 newtons. So the 6 Newton force is actually doing more work than the 8 Newton force. So why wouldn't I just always push in the direction? Well, we'll talk about that as we talk about, or we've talked about it with friction, right? Maybe it's too hard to push that 6 newtons, so I can pull up at 8 newtons to reduce friction, right? There's all these different things. The more and more we understand about physics, the more complicated we can make our questions. So here's a partner problem that we'll take a look at during class. We have, again, a force, but now it's exerted at a 45-degree angle, pulling on a suitcase. So if you wanted to take a look at that at all, you can go ahead. That's my suitcase, believe it or not. That's 20 newtons. And how much work does tension do if the suitcase is pulled 100 newtons? So we'll take a look at that, but that's going to use the work equals force times distance, and we're just solving for the work again. Some forces do no work. A force does no work on an object if the object doesn't undergo a displacement. If I push a car that's in park and I can't get it to move, as hard as it feels like I'm working, there's no kinetic energy, so I'm not actually doing any work. Again, we've talked about this. The force is perpendicular to the displacement, so if the object's moving to the right, but I'm pulling up, I'm technically not doing any work. And again, with the displacement, the part on which the part of the object on which the force acts undergoes no displacement, even if other parts do move. So if I push on something else that's not moving, I'm not doing any work. So that was your quick little introduction into work. So we've gotten an overview of energy, an introduction, and the explanation of the quantification of work. And now we're going to get into types of energy, and we'll be able to start solving problems. And we'll do that in the next segment.